Welcome to the SEG Near Surface Geophysics Technical Section Global Subcommittee. And today we have a presentation by Dr. Nalima Satem. She is currently a professor in the Department of Civil Engineering at IIT Indore, and she holds a PhD and an MTech from IIT Delhi and a BTech from SV University Tirupati. For joining IIT Indore, she served as an assistant professor at the Earthquake Engineering Research Center, IIT Hyderabad. Dr. Satem was also a visiting professor at Kyushu University and University of Stuttgart and the University of Tokyo. And she is actively involved in teaching, research, and consultancy in geotechnical engineering. Her expertise lies in geotechnical earthquake engineering, microresonation, site response studies, landslide hazard, monitoring, microseismic data processing, rock engineering. Dr. Satem received research grants from DST, MHRD, AICTE, ITRA, DAE, NIOT, NRDM, and she's published more than 150 papers in international and national journals and conferences. Her research publications have received Best Papers awards from IGS, AGU, and IIT Indore. She is the co-opted member of PAC Civil and Mechanical Engineering, SERB, DST. Between 2015 and 2018, she has been the chairperson of the selection committee for MEX scholarships, that's MEXT, of Japan since 2015. She is a recipient of IEI Young Engineers Awards in 2011, BRNS Young Scientist Research Award in 2011, AICTE Career Award 2012, and JSPS Fellowship in 2013, Young Women's Engineer Award from INWES in 2012, CIDC Vishwakarma Award in 2021, and ISET Shamir Prakash Mid-Career Research Award in 2022, IGS Sardar Rashem Singh Memorial Award in 2022, Best Woman Researcher in Geotechnical Engineering Award in 2022, and she is presently the editorial board member of several reputed journals, including Nature Scientific Reports, Journal Rock Mechanics, and Geotechnical Engineering, etc. So without further ado, let's welcome Dr. Nalima Satem for our presentation today. Thank you.
So thank you so much, Dori, and for your kind introduction. First of all, good evening, everyone from India, and good morning to other parts of the world. Thank you so much for inviting me. So my sincere thanks to Dr. Krishnaya for nominating my name for this lecture series. So thanks to him, and thanks to Laurie, especially because you have taken all the efforts in organizing this talk. So my topic today is on landslide hazards in the Western Himalayas, where I've been working in a place called Joshimath, which has been very serious in terms of landslides and subsidence issue. We started this project almost like 2.5 years back with the support of Department of Science and Technology, Government of India. I'm sorry, I'm just doing this presentation from some other system, which is my doctor's iPad, because of some issue in my laptop. So this is the overview of my talk for today's presentation. So I'd like to give a brief introduction about this particular area, because Himalaya is such a younger formation, such a fragile formations, and it is a hotspot for many geohazards like earthquakes, landslides, floods, and something like that, and a combined hazard as well. So we are trying to understand a particular combined phenomena here. This is one of the novel, I can say, because we are trying to address this particular study area has seismic activity and also rainfall. In addition to that, it also has a snowfall. So we are trying to understand the landslide, especially hazard, through modeling, and we have done several modeling aspects, and we also done a lot of site specific survey, like geophysical surveys have been conducted. And the most interesting part is like we are doing the real time monitoring of a particular slope. So I would like to explain this by converging. So first one is like we did on the susceptibility mapping for the entire district. When I got this project, from my sponsor, that's the government of India. So they just said like, you do something, when I presented my objectives, so they said like, you take an area only in Uttarakhand, because I propose some other place. So of course I should thank the reviewers of that committee, who suggested me to go for the Uttarakhand, because this particular area is been in a very very big issue in the recent past after we started monitoring this. So in every sense, like I feel like this particular piece of work is very close to my heart, and I should acknowledge the PhD student, who is also Prime Minister Research Fellow at IIT Indore, who has done extensive work in this particular project. So coming to the overview, so I'll be starting on the Chamoli district. As I said, like they said, like you take some area in the Uttarakhand. Uttarakhand itself is a very big state in the country, and within that state we are not sure that in such a big area where to put your monitoring, because our idea of doing this hazard is to understand the physics behind the landslide phenomena. So for that, like I would like to do the monitoring part, and capture what is a combined effect with microseismic monitoring and also with different sensor networks. So started like, because we are not sure where I'm going to instrument my slope. So what I did is like, we have considered a particular district which is more vulnerable in the entire state, that is Uttarakhand. In that, like I had taken a Chamoli district. So then like we try to converge by doing the detailed study. As I said, this particular area is having rainfall combined landslide hazard, I can say, and it is also hotspot of seismic activity. And in addition to that, this also has a snow. So what we have tried to consider is like, we want to understand all the three. Okay, so in monsoon there's a rainfall, and then followed by snowfall, and if there is any microseismic activity even less than 2.5 also, it can lead a bigger landslide disaster. So we will try to understand the combined aspects. So then the rainfall thresholds we started again for the entire district, because we are not sure like where to start the monitoring part. And in our thing, we started the monitoring in the first year of starting of the project. And then the another thing is like, see, it's such a highly varied geologically, geomorphologically. Every few meters there is a change in thickness also. So what we try to do is like, we don't have that much bore log data, and making a bore log or any kind of geophysical test to understand the thickness like ERT or any other testing for such a larger area is also not feasible. So what we have done is like, we did some modeling also, and here soil thickness mapping for the Joshimath region and the surrounding regions we have done. So using some modeling techniques, I'll explain that using Monte Carlo simulations and also some machine learning algorithms, and then we validated that by making some bore logs. So we, by doing this, this LSM, like susceptibility mapping, we incorporated using Monte Carlo simulations in the TRA-GeoMars. This is the novelty of the work, and I can proudly say that nobody has done this. This integration of like susceptibility, because we would like to bring a dynamic susceptibility, okay, wherein like it depends on many factors. So we'd like to bring out a operationally dynamic susceptibility map for that particular study area. For that, we are also use TRA-GRS model, and then the final outcome should be development of the operational early warning system for this region. So coming back, so many of my friends who are here from India know like what is the seriousness of this issue in this particular part of the Himalayan towns. So if you look at the database of the non-seismic landslides, so this is between 2004 to 2016, almost like 60,000 people lost their life. Several landslides, around 5,000 landslide events, and 75% of the landslides, major landslides, are from the Asian countries. And India being a large country, so we do have like witness several landslides every year. Not only in the Himalayas, we also have Eastern Ghats and Western Ghats, which have been severely affected because of the landslides. So for us, it's not only about loss of life or any other thing or infrastructure. For us, because loss of land is also major concern. Why? Because most of these regions are also depend. Many people, farmers are dependent on their land, agricultural land, very fertile lands, and if they lose their land, it's like losing their life. So losing a land is also serious concern for us. So then global database, if you see for seismic landslides, so again, there are like 54% of the events are from the Asian countries. And if you look at the Indian subcontinent, like most of the triggering factors are rainfall and earthquake are combined, especially in the Himalayan towns. And they are highly landslide susceptible areas. If you look at, can be classified into Himalayan regions, where my this particular case study is focusing for today's talk. We also been working on Western Ghats and Eastern Ghats partially. So this is the location map of my study region. It's a state called Uttarakhand, which is a very, very famous for pilgrimage in the country. Everybody will be interested to go to this place because there's like very Hindu spiritual temples are there. And among the, if you look at this, is extremely in the Western Himalayas. And then among the most seismic active regions in the world, as per our Indian seismic code, it's falling between seismic zone 4 and 5. And of course, it is in the central Himalayan gap. So this particular piece of work, we have a collaborator from Borders BRO, Border Source Organization, who helped us with some of the support that's required at the site, because the site is very, very challenging. You can see some of the photographs also. So we made a first visit. We are not understanding like where to, you can see the kind of geomaterial. It is like highly fragile material. It appears like rock if you see from little far, but when you go and touch it, it comes like a powder. So because of the tectonics, the rock mass is highly crushed in this region. For the last 1.5 years, I can say there's a serious concern for this landslide subsidence or the ground subsidence in the town Joshimath. These are some of the photographs, and it's sinking. Okay, let me tell you, there has been almost like 1,000 families tried to evacuated with the help of the government of India in this from this town, because there is like very alarming situation. People were like panic, and many people try to get evacuated from that town. Let me tell you, it's not just only the Joshimath town. Maybe 200 plus towns in this Himalayan towns are there which have been thinking like this. I can say that Kalimpong is also facing the similar issue. So it's not just only Joshimath, but Joshimath was into the news in the recent past because of whatever the reasons. So ground subsidence in this area was a big problem. It's not a sudden failure, it's a sort of progressive failure kind of phenomena, and persistent sinking and subsidence has been observed as per the GIS report also. So this particular, some of the photographs again. So this particular town, and it's very it's lying between the main Himalayan fold, and then it's a thick deposit also, because maybe in the past there may be landslide and it got deposited. So this is sitting on a thick deposit of colluvium and the whole landslide deposit. So that is one of the, because it's a very loose and unconsolidated material, maybe there is a subsidence issues also there. So another reason primarily identified because of this is like internal erosion. So I can say that this is a drainage problem because of the subsurface drainage issues. So because people are building urban infrastructure, or maybe in general also a lot of infrastructure is happening in the Himalayan towns. So maybe because of that, there's a drainage concern or the issues. So that may be the another major reason for this kind of subsidence phenomena. So with this background, So we started with a landslide susceptibility map for the entire Chamoli district. So the outline one is a state of Uttarakhand, and we have selected a particular district which is called Chamoli district. And initially we performed the landslide susceptibility for this particular district because of the considering the geological vulnerability in terms of steep slopes or fragile geological formation and active tectonic activity, which generally increases the susceptibility of the landslides. Historical incidents were also being considered, and human settlements and infrastructure, because rapid urbanization and development has been identified in this area. So, which can consider that there's a risk to inform land use planning and infrastructure decisions. Ecological importance was considered, tourism and economic impact, and also the climate change. So climate change is expected to increase the frequency and intensity of the extreme weather events, so which can increase the risk because of the landslide. So initial layers or input layers, initially we prepared this inventory using various sources, reports, Google Earth maps, site visits, satellite images, and then we prepared inventory which had like initially around 363 points. We have tried to consider both point data and also the aerial data, and many of these locations they get reactivated every year. So, and the time duration what we consider from the year 2000 to 2023, and we considered 14 conditioning factors for making the LSM, which included parameters like geology, geomorphology, PGA, rainfall, and NDVI, distance from the road, lineaments, and the streams, etc. So these were the input maps which we prepared it. You can see here from one, like this aspect layer, then this complete study area was divided into 8, and then aspects was varying between 0 to 360 degrees, and then we have like SPI map, and we had this rainfall NDVA map, PGA values of this region were like as high as 0.49 G, and then slope map, etc. Then we considered the pixel based as well as the slope unit based inputs for LSM. So in previous studies, if you look at in the literature, slope unit based inputs, they have given better results compared to the pixel based. So, but for this reason, we prepared both slope unit map for Chamoli, and then we are the first ones I can say in the country to prepare a slope unit map of the complete Uttarakhand state. So this is the one, and most of the work has been published. I will be happy to share some of the papers if anybody is interested. Then, equal number of landslides and non-landslide points were considered for the study, and then we prepared the final inventory. After preparing the final inventory, what we have done is like 80% of the data we use for training because we use machine learning algorithms, and 20% we use it for testing. Then based on the different machine algorithm models, like using Bayes theorem, SVM, KNN, and RF models, so we have prepared LSM map for using the different algorithms, and of course they had been validated. So here is the validation. What we find is like highest landslide prediction accuracy, almost like 98% was obtained using the random forest approach. So when we made it 80% for training and 20% for the validating. And then LSM was done using RF for both pixel based and slope unit based inputs as it's shown here. And the results of this LSM based on different machine learning models were suggested very high to high susceptibility of landslides in and around the Joshimath region and southern east part of the Chamoli district. As you can see here, based upon the susceptibility mapping, where there were very higher susceptibility was there. And in the second part, we tried to look at only the rainfall, and then later we integrated that. So there are some figure 25. I don't know why it's missing here. I can share the presentation if anybody wanted. So what we have done is like we have derived rainfall thresholds using various methods, both probabilistic and empirical thresholds for the entire Chamoli district. And in the study area, throughout the time period, like from the year 2000 to 2023, as I said, like we have considered all the landslide events, and in total all the like rainfall events also, which were almost 74,000 something. So huge amount of data has been used, and rainfall thresholds have been made. Here it is a probabilistic approach where one-dimensional and two-dimensional Bayes theorem has been applied for probabilistic landslide, thresholds, rainfall thresholds. So here is the one-dimensional and the two-dimensional where the control probability has been tried to calculate, and AUC analysis for this probabilistic thresholds were also being carried out. Then we applied the sigma model. So sigma model, we also developed this threshold using the sigma model because sigma model has been developed from University of Florence by my collaborators. So what we have done is like we took that base sigma model and we have incorporated the site specific parameters which can shoot to this particular study area, which will help for development of the early warning system, as you see here. And after evaluating and validating different rainfall thresholds, we observe that sigma model based thresholds are best suited for development of the warning system. As you see here, there is like empirical, we have, as I applied, like we have empirical ED, probability ED, probability EI. So different threshold models have been applied, but when we look at the results, in terms of statistical comparisons, we got like this particular one is taking more, giving more accuracy, because here we have taken the soil wetness and other infiltration parameters have been considered site specific values. So that's where, like, when we could incorporate those values, this particular model was giving us better results. In the next one, we want to make the soil thickness map for this particular Joshimat town. So precisely determining the thickness of the soil, which is very essential parameter in this kind of modeling. So it presents difficulties when we apply to heterogenic large scale areas, because this is also like very geomorphologically, geologically, that's like very highly heterogeneous region. So current prediction models, whatever we had in the literature, they primarily concentrate on shallow soil depths and they lack comprehensive spatial coverage. So in this one, what we did is like we address this limitation by presenting the results of the soil thickness assessment along three important roads in the Joshimat region. The first one is a Joshimat Badnidar road, and the second one Joshimat Malari road, and the third one is Joshimat Pipalkoti road. So initially, we were not sure like where to start with. Like we have considered these three roads, and geological map identified 5 distinct geological formations which are present in the study as it's shown in the table 5. And using this information as a foundation, the study area was partitioned into 5 distinct units which are demarcated by the boundaries of these geological formations as it is shown in the figure number 30 in the top. So these are the 5 different areas and we demarcated that. Then this is actually what we have done in landslide modeling for soil thickness. So 3 different methods are we try to incorporate geological, geomorphological data as an input to obtain the soil thickness map. And you can see here the first one is basically it's a customized version of the conventional. This was the first one. It's a customized version of the conventional geomorphological index soil thickness, which is called GAST model. And this one we modified specifically for the peculiarities of this particular study area. And in the second one, so this is actually GAST model with Monte Carlo simulations. So MCS, GAST, MCS model, this one. And then third one is like we applied GAST model with random forest algorithm. So what happens in this one, I'll explain one by one. So in the first one, which is a conventional GAST model, the factor C, this is the factor C, which addresses the influence of the surface curvature of the soil thickness. For that, like DM was used to extract the profile curvature. So we have done some drone surveys in this region for each pixel, which was used to calculate this factor C. Similarly, in the figure also, the other figure you can see here, like for larger proportions, especially these values were focused within that narrow interval. And so the above equation, for C, which has been here, sorry. So there is an equation here for C, which is not visible here. So we use that equation for calculating this particular site-specific value, and then the incorporation of spatial information in this GST model allows for a comprehensive understanding of how the location of point in relation to another inside the hill slope profile influences the distribution of the soil. So then determination of P also involves utilizing the DM to combine the shortest distance. Since we are not getting the DM, proper DM from the LSPER data, so we have carried out the drone surveys. And then I'm sorry, here also equation S is not coming. So there is another factor. This is the third factor, which take into account the factor S, which we call influence of slope inclination, which is also plays a significant role in erosion phenomena and loss of soil. So in this investigation, we adjusted this factor S formulation for better accommodate the steep terrain characteristics of the Joshimath region. And then a new forecasting model like JST MCS model was also developed, which we generate to improve the soil thickness map, which could take into the uncertainties which are associated in the distribution of different soil properties. So then GST Monte Carlo simulation model incorporated Latin hypercube sampling, which is based Monte Carlo simulation to model these uncertainties, which will provide more robust prediction of the soil thickness. So these are some of the results of the soil thickness map using 3 different approaches. So after doing this, these were the results, and then we tried to generate the map also. You can see here, these are the figures that the maps generated by GST model and the GST Monte Carlo simulation model, then GST RF model also. And the alignment with this borehole data, because VRO was doing a lot of work at that particular site for some of the landslide mitigation, etc. So we got almost like 52 boreholes, and along these 3 roads, so which we used it for, which also suggests that GST MCS model provide a more accurate representation. So after our results, we could validate that with the bore log data. And on the other side, GST RF model was exhibiting a broader range of soil depth ranging from 2 to 30 meter, whereas like RF model was, generally has a higher mean and median values with a lower standard deviation, which is like more restricted range compared to the other models. These are the findings that which implies that the GST Monte Carlo simulation model significantly enhances the accuracy and reliability of the predicted data. So we have done this for first initially for these 3 roads, and then which can be extrapolated for the different other parts of the state. So we have done only this one because our idea of monitoring is in some place which is in this among these 3 roads. So, and also there are different factors have been considered for selection of the monitoring, including that it should be a virgin slope, it should not have been done any mitigation measures, and other safety issues, electricity, etc. So that, finally this GST RF model was demonstrating, remarkable validations with respect to the statistics compared to the other 2 models, as I explained. So for validation, we have carried out, of course, this is also seismically active region. So what we have done is we have done different geophysical tests, like we have carried out ERT, we also did MSW. Okay, so finally we selected a slope for monitoring. It's called a Lambagad village, so which is very, very fragile slope. You can see here some of the images over here, and we have done the MSW to understand whatever the shear wave velocity profile of this particular region, because we have also been doing seismic signal processing for landslide susceptibility. So for this one, the bedrock was encountered between 20 to 30 meters depth, and which was in line with our soil thickness map, which we obtained using the previous study GST RF model. Then we performed the landslide susceptibility map by incorporating the Monte Carlo simulation in the TRHGS model for the Joshimath Badrinath road. Among these 3 roads, we finally converged to a particular road, for carrying out this, so that that can be extrapolated for the different parts. So this particular stretch has been considered for carrying out the TRAGRS model. So these are the inputs or the details of this method which we have taken. So this is the methodology in which we can obtain factor of safety, PWP, and failure depths as the output. And here we spatial variation of the geotechnical parameters was modeled using Monte Carlo simulation, and the soil thickness, whatever we have done in the previous slides, whichever I explained, that we have considered here and incorporated in this one TRGRS method. So these were the input layers, you can see here slope angle, quotient, unit weight. Okay, so this we have developed for this particular road where we are going to monitor, and then including the saturated diffusion coefficient, hydraulic conductivity. So these layers have been used for carrying out the TRGRS model. So this is the soil thickness map which obtained from the JST MCS model, which was been considered in this analysis. And finally, the final results which show that major portion of the region is highly vulnerable to the landslide failure. Here we obtained an accuracy around 93%, and we are, as I said, with respect to 3 different parameters like factor of safety, pore water pressures, and also the depth. Okay, so we have tried to present the results. Then finally, development of operational early warning system for this particular Joshimath, that is especially for the Lambagat village near Joshimath. With the experience, we had a previous experience in developing the regional scale forecast for Kerala, especially for 2 districts in Kerala, Wayanad and Idukki, and a local scale forecast for Kalimpong. What we did here in this particular study was we framed a more complex framework for Uttarakhand, considering both regional and the local scale factors. So this case of Uttarakhand is more complex, as the triggering factors are not only rainfall alone, like in Western Ghats or in Kalimpong, it also have an earthquake. So here we collected the data. Data phase itself is difficult, and the seismic data we have considered. First, we understand that high seismic hazard zones and seismically induced landslide hazard zones, and then we evaluated the distribution of rainfall. Then based on these observations, we selected the Joshimath for real-time monitoring. Unlike in our previous study, Kalimpong, where we had only tilt sensors and moisture sensors, here we have a very strong, dense network of sensors to get more information about the complete movement of this particular slope in the Lambagat. So this installation, we had sensors both below the ground, like in the borelog, and also surface sensors. We have carried out in a better way after conducting aerial survey and the detailed slope stability analysis also, and this helped us in identifying the critical slip surface and fixing the depth of installation of the sensors. The location is exactly along the Chardham Yatra road, and many people may be aware of this road. And we also installed a camera, high-speed camera at the site to study the influence of vibrations which are induced by the construction activities or some vehicles, because this road has been extensively used by military operations and for the pilgrimage purpose. So this is that road where we finally selected our site for monitoring. In Chamoli district, this Joshimath town was selected after carrying out detailed study. As I said, our collaborator BRO, who is supporting agency for logistic help at the site for real-time monitoring. And then Joshimath Badrinath, Joshimath Malari road were initially selected, but Joshimath Badrinath road, which is a part of this NH58, and then Joshimath Malari road were very important roads, as I said, for both military and the pilgrimage purpose. Every year we see large number of landslides occurring in this particular road. So initially we have selected 6 sites where to monitor, but considering several factors like accessibility or availability of electricity, even the safety, so we converged to 1. So these were the 6 different sites. We initially did the analysis, slope stability analysis. We have collected the samples from these sites because we need the slip circle, and then we try to do all the things, but later we did it only for the site number 6. So these were the field geotechnical data after collecting the samples. So the factors that we consider for selection of the site are converging to one side because, as I said, the safety is the major concern. Maintenance also, and now we have a volunteer there who will help us with the maintenance issues, and electricity availability. Our electricity connection, the cable itself took a few kilometers, okay, point, and we have an electricity point on our name there. Then availability of nearby town or habitation, I can say, wherein there is accessibility to the site. So considering all these factors, we finally converge to this particular slope. So this is actually the slope profile, and you can see here these are the dots where we made the bore log, and this is the sensor locations, this particular figure, and we have done the UAV survey as well for this. You can see here the average position was around 15 kilonewton per square meter, and the phi value was mostly 34 to 36. So these were we obtained rock cores from bore logs. We have done bore logs, and the bore holes were around 150 diameter, and we collected the samples and tested that in our lab, etc. So then drone survey was carried out for this particular slope at a Lambergate landslide zone. This is the high resolution aerial image of the landslide area. And then after these images were used to create the 3D DEM for this particular landslide and to identify the areas of damage and potential risk. These images actually were very useful, basically, not only to create the topographic maps of the this particular slope where we are going to monitor, it is also useful in identifying the drainage pattern and potential water accumulation points. So because these are the most, this kind of drainage accumulation or the water accumulation points on the top of the slope, really increase the risk of slide. And we conducted the survey over a period of 2 days, and the data collected was analyzed using the standard GIS softwares, and the survey identified several potential risks for further landslide, including area where there are cracks in the slope and there are potential water accumulation. So many sites are most of the sites mitigation measures have been taken. So we want a fragile slope also, because if it is been mitigation measures have been taken, so we may not get the data. So we want a virgin slope, so we could get that in this site number 6. So these are some of the photos of our monitoring station. I don't know why the image got rotated. So this is an automatic weather station which has been instrumented at this location, and all the sensors are transferring data every 10 minutes via VSAT. And the data, we can access it from the cloud directly or via the receiver which we installed at our IIT Indore campus. We also developed an indigenous landslide monitoring and early warning system, wherein the data of each census we can study on a website. As you see here in the right side, this has been, we have this, and then in each parameter, every bore log, right, we can get the pore water pressure, we can get the soil tension, okay, and the extensometers have been there, inclinometers were there. So all this data is coming every 10 minutes, and interface of the website, we can see it on the top of the right corner, like this one, you can get a direct curve like this, selecting the location and the sensor parameter, so the data can be accessed. Finally, this is the conceptual framework for the slope scale early warning generation, or the development of early warning system, which we did it through hydrological modeling and slope stability analysis. So initiated by essential monitoring phase, data collection is of course very important for subsequent modeling, and monitoring data which encompasses a spectrum of hydrological parameters ranging from pore water pressure profile to soil water content data, which complemented by the meteorological data. So considering precipitation, temperature, and relative humidity as well. And the data set as an input for hydrological modeling, because for me, in this, it's not just only the geotechnical or geological data. We have to consider the hydrological data as well, because landslide hydrology is something very, I personally feel like we are missing that as a geotechnical engineer. So wherein we try to incorporate that, and data set as an input for hydrological modeling with geotechnical parameters, which we have got it from lab and the field both. And this calibration also refines hydraulic conditions for the failure. This standard emphasizes the importance, which of ensuring the minimum factor of safety, various slope types, and including natural and cut slopes, or even the debris soils. So in the predictive phase itself, the projected data of the precipitation or pore water pressures, factor of safeties, we can use that as input variable for training, using machine learning algorithms, which we have done. And the objective is basically to forecast the time period when the slope is unstable. So when it exceeds some established threshold, so or detecting the factor of safeties which are less than 1.5, so then we can try to give a warning. So or which can necessitate the activation of warning protocols or the emergency plans. So this is how we have been doing, integrating monitoring, modeling, and of course the forecasting, all three levels to make a slope scale warning system. So this is some more data where we use non-calibrated and calibrated both. So which almost total of 3 iterations, each incorporating distinct set of input like rainfall and climate data, rainfall, climate, and vegetation data. Because this is also you can see here NC and C, both calibrated and non-calibrated, and 3 different approaches, simulations we have considered here. Again, I can say many people have considered only rainfall or maximum rainfall and climate data from some work from Italy, but rainfall, climate, and vegetation at the site specific, vegetation condition was not been considered. So calibrating this hydrological model, as you can see here, in different simulations, particularly in shallow depths, exhibit robust performance, especially in this particular study region. And also we try to understand the significance of interacting the climatic drivers and the vegetation dynamics. So by conducting a comparative analysis between the simulation results and the in situ measurements, this using Taylor diagrams for more clarity. And a critical assessment was conducted to evaluate the efficacy of this chosen hydrological model across different temporal scopes, for 6 months, 12 months, and etc. Temporal performance evaluation over different time frames. So it identified that 12-month simulations were consistently, in good correlation with the actual data. So this is our Taylor diagrams. Then furthermore, of course, as I said, we also applied advanced machine learning approach for utilizing the random forest algorithm, was implemented to predict the factor of safety. Because see, there are different dynamic factors. Rainfall is highly dynamic, right? Earthquake is highly dynamic. So considering those dynamic parameters, if you can forecast based upon your modeling, considering the site specific data, if you can forecast the factor of safety for the next 6 months or next 1 year, and then if you can predict that, then that is one of the very good. So what we have tried to do here is across all the cases, factor of safety consistency remained below the critical threshold, which we defined as 1.5 in this particular case. Objective was basically to forecast the time period when slope is unstable or prone to manifest, which can exceed that threshold of 1.5 for activating the warning protocol. So we also did, as I said, we also instrumented microseismic monitoring at the site, in addition to extensometers, inclinometers, tilt meters, rock strain gauges, etc. So based upon we also try to apply some of the seismic signal processing. We had in sometime back in 2021 February, there was a major event, Dauliganga event. Some of you might have read this, who are from outside country. So it was a massive rock slide event, which resulted more than 200 casualties, and also estimated something around 200 million US dollars of infrastructure establishment. So this is, I can say, the first in India to employ the seismic signal processing methods to study this kind of event dynamics. So what we have done here is this has been published in the Journal of Asian Earth Sciences. So we tried to find out that hazard chain, okay, using this data. So the complete hazard chain was understood and the complete event dynamics were being understood. And this particular study provides a better insight into the hazard event characterization and interpretation methodology, because when we started the work this event happened, so we try to consider this particular study also considering seismic signal processing. Now we have micro seismic monitoring also, and along with that we are also trying to capture the vehicular movement through our cameras, so that that ambient noise was also being can be able find it out, and then actual signal can be picked up. So there's still monitoring data. We are working on the analysis part of it, and that's all. This is ongoing work. We have been working for the last around 2.5 years now. So still some more time to complete the project. So thank you so much. So most of the work has been already been published. So interested can contact me. I'll be very happy to share. With this, thank you so much. Thanks to organizers, and my special thanks to Dr. Krishna sir.
Thank you. Thank you so much, Dr. Nalima Sateen. We have time for some questions. If you would like to ask questions, you can raise your hand. The raise hand button is at the top of your screen in the toolbar. But excellent work. Thank you for your presentation and documenting all of the hard work that you've done, you and your team, to safeguard the well-being and identify factors that will contribute to landslides, and try to be able to quantify those.
Hi, thank you, Nilima, for this very interesting talk. I am not a specialist at all, so I just wanted to know, because you show many maps with many parameters, and I would like to know how you obtain those maps. Do you interpolate between borehole measurements, or do you have some other source for your data?
No. Boreholes we used only for validating the soil thickness map, which we generated through landslide modeling. But mostly these maps have been developed through the data sets or inventory that we prepared. We had several reports available, and we worked on the data.
Okay, I understand. Thank you.
Thank you.
I just raised my hand just to say thanks to Dr. Nilima Satyam accepting our invitation in a short notice. So I thank her on behalf of our global geophysical technical subcommittee. Thanks, ma'am, for your accepting invitation and delivering a very good talk.
So thanks to you for nominating my name, and thank you so much.
Yeah, Dr. Laurie, one more question to Dr. Nilima Satyam. Ma'am, can you use this fiber optics technique for this thing?
Sir, but that is very expensive. We are doing one slope monitoring for a mine company using FBG. But sir, that's been too expensive. We cannot cover larger areas. So we didn't use FBG for landslides.
Okay. Thank you.
I hope I'm audible to everyone.
Yes.
Okay. Thank you, ma'am, for the wonderful lecture. Ma'am, I would like to ask you, there are certain areas like Joshimath is the region where there is a snow season is also there. And there are certain like precipitation sometimes also happens. So I have just observed, and I have discussed someone that they said that nowadays the precipitation patterns in the Himalayas, especially in the this northwest Himalaya, they are little bit changing in terms of, let's say, intensity wise as well as with the elevation wise. Where earlier there was no precipitation in terms of rainfall, now they have rainfall. Earlier there was snow precipitation form was there. So do you have any observation of like this, or what things we can consider while installing or while monitoring such kind of parameters?
No, it's very important actually. We also do it. That's why we instrumented our weather station in the starting of the study itself, because from rainfall data, what we get it from IMD, it gives only the rainfall, and some rain gauge will be there, which may be around 15 kilometers away also, and you don't get it that site-specific, rain gauge, because within few kilometers there is a huge variation in the rainfall. Rainfall is highly dynamic. It's not just only intensity actually. So there are different parameters of rainfall are required. So what we try to consider here is like because there are some uncertainties associated with this. Of course, we instrumented our weather station, which will take care both rainfall and also the snowfall aspects. Because we have done for the last 2.5 years continuous monitoring is there, we could consider that, because finally your pore waters is something important for us, right? And that site specific pore water characteristics of that particular slope has to be considered for your complete modeling studies. So we cannot do monitoring for larger area. So that's why what we did is like we did the modeling and we also did the LSM for larger area. For validation, we are using the monitoring. Monitoring, we are not doing it for developing the early warning system. To develop an early warning system at any scale, slope scale, local scale, or regional scale, monitoring should be used, or like we have been doing this since 2016. We are monitoring, we are using only for validation. Okay, and I hope I cleared. Not only in Himalayan region, the rainfall is very different, or maybe because of climate change factors, etc. So every part of the thing. When we started in Kerala in 2018, what happened was like when we looked at the landslide susceptibility maps already with KSDMA, wherever there was a no susceptibility or less landslide susceptibility, there it was huge hazard. Like landslide hazard was high in that region. So landslide susceptibility maps, what we have prepared few years back, are not actually correct. So we have to develop a dynamic landslide susceptibility map at panchayat scale or some local scale, because finally the based upon the thresholds and other things, we are not the authorized people to give a warning, right? Finally, you have to hand it over to somebody. So in our case, especially in the Western Ghats, we did that to work closely with KSDMA and to develop a dynamic landslide susceptibility maps at the panchayat scale. So these are all like with the time, taking the real time rainfall data, it changes, and also we have to consider the site characteristics also, especially the geotechnical parameters. And hydrological, geomorphological, geohydrological, geotechnical data of that specific to that area, because there are different factors, infiltration characteristics, soil wetness, you need to consider when you are developing it.
Yeah, thank you, man. Thank you. PJ value is also means necessary to be monitored continuously.
In this case, PJ has also been considered, and that part I didn't put in this slide, but we have done the PGA analysis. Of course, a lot of people have already worked on the PGA part of, but we have done using Aries intensity approach because of lack of sufficient data. So we did that. That part I didn't add it, but it's been there. You can check.
Okay.
Student
Okay.
Kunal Gupta. Okay, his papers are all there, and you can see my Google Scholar also. So you can find those. Yes.
Sure, man. Sure. I'll contact if there will be any. Thank you. Thank you.
Yeah, thank you so much.
Thank you so much, Dr. Satim, for such a thorough presentation. A very nice question and answer session. I speak for all of the global subcommittee that thank you for accepting this offer to present for us. Always a great learning opportunity. So thank you very much. Thank you everyone for attending.
Thank you everyone, and thanks Laurie for hosting me. So with your permission, I can leave, right?
Yes.
Thank you.
You're welcome.